Hello, my name is Jasmine Alexander. I am this week's project manager for the INDE 6332 course, Engineering Project Management. This is Group 3, the Six Sigmas, assignment number 6, which is Network and Critical Path. My team members include Wesley Bennett, Daniel Leach, Mohammed Farhan Mahudin, Gauss Shaikh, and Isabel Tai. The background for this project surrounds the concept of scheduling. It's a conversion of a project plan into an operating timetable and is used to monitor and control project activity. We track this activity through what is called networks. For this assignment, we'll be creating a network based on the Gantt chart and work breakdown structure for the Texas Wildlife Vessel previously established in a previous assignment. Within the network, we will have each node labeled, and it will be labeled based on the earliest start time, earliest finish time, and latest finish time for each task. We will then solve for the critical path of the network and provide the results. For our approach, the first thing we did was created a table in Excel to establish the basis for a network. We then took that work breakdown structure and highlighted each high-level task. We then added columns for a number of days to complete each task. Within these tasks, we had a column for optimistic days to complete a task, pessimistic days, and likely days. Using the previously established work breakdown structure and Gantt chart, we completed the chart for each task. We used the previous results from the Gantt chart and set that as the basis for the time frames for the likely column for completion task. And then we used engineering judgment to determine pessimistic and optimistic completion days for each task. And then we used the Gantt chart and established predecessor for each critical task within the project. For our continued approach, we then had to calculate the activity times. We did this using beta distribution by solving for effective time and variance using the following formulas, where A equals optimistic, B is pessimistic, and M is likely. The formula for effective time is A plus 4M plus B divided by 6, and variance was B minus A divided by 6 to the second power. We determined the critical path using the forward pass method and backward pass method, establishing the earliest start and finish and latest start and finish dates. Highlighted at the top of this chart were the columns used for the variables to solve for the effective times and variances, and formulas were created within the Excel sheet. This slide displays the combination of the approaches I mentioned previously. Each column is filled out based on predecessors, optimistic time frames for each task, likely tasks, and the pessimistic time frames. And then the estimated time and variance were solved on the right. We used this information as the basis to label the nodes within our network. Here is a result of the calculations from the previous table to give us a network. Our network starts with the project start, which starts on day 0, and the first task is developing a work breakdown structure, which from our table tells us that the expected completion time for this task is 5 days, with the variance of 0.44, which is labeled inside the node. This day 5 is then labeled on the top right of the node. Because this is the only predecessor, it then goes into task 2, which is to establish the LRC. We established from our previous table that this task takes 1.25 days. We take day 5 and add the 1.25 days to give us a total of 6.25 days located in the right of that node. This approach is used throughout the table to establish the earliest start and the finish of each node. The continued results on this slide show the successors of the previous steps, including their predecessors as well as their completion days. Here are the continued results from the previous slide of the continued network that shows the end of our project, which would be the boat delivery. Circled here is the critical time established based off of the forward pass method, which from this network tells us that the critical time to complete this project is 80.01 days. Here's our final result of an overview of our network showing each critical step as well as the predecessors and successors to each task. Highlighted red is the critical path that the project has to follow with its activities in order to stay on task to complete this project by the set day. The work breakdown network, labeled below, is a network consisting of each high-level activity. All of the shared predecessors have been combined into one step. In this instance, the system design and spec, the procurement, the in-house fabrication, the installation and assembly, and the sea trial have all been combined into individual steps. This final results slide shows the mathematical calculations that support our result for the critical time and the critical path. On the right is a table that is modified from our original table that included all of the calculations for our time estimates. A slack table was included, which is calculated using the latest start time, the earliest start time, to calculate the total slack for each activity. Using the example nodes at the bottom, the installation of above deck electrical system has an earliest start date of day 73.01 and it has a latest start date of day 73.01. When you subtract those two, you get an answer of 0, which proves to us that the earliest start and latest start is a critical time for this task. You can see in this table that the column has been labeled green to indicate that it is critical. However, in the example on the right, the installation of the above deck sanitation system, the start date for the earliest start day is day 75.18 and the latest start day is day 76.84. When you subtract the two of those, you get 1.66. This proves that this task is not critical. Using this method for each activity, it was determined that the critical time for this project was 80.01 days and the critical path is task 1, 2, 3, 4, 13, 15, 23, 26, 34, 35, and 39. These can be seen in the final display of the network on the previous slide. Thank you.